Today we're very happy to have Wailing Xin and Chenyu Huang. Wailing is an MR student and research assistant at the NUS Ideas Lab, advised by Rudy Staufs and Adrian Chong. He develops autonomous urban agents by integrating CNN-based spatial perception with LLM reasoning to scale building intelligence toward urban environmental resilience. And Chen Yu is a PhD candidate in architecture at Zhongxi University, advised by Associate Professors Chihuai Yao and Xi Huang. His research lies at the intersection of AI for science and urban complex systems, with a focus on spatio-temporal modeling of physical fields and performance-driven urban design. His doctoral research investigates the scaling laws of urban non-equilibrium thermodynamic systems. He is the recipient of the CAADRIA Young Awards for his outstanding contributions to computational design in Asia. And with that, I'm happy to hand over the mic to you and looking forward to your talk.
Okay, thank you, Julia, for your kind introduction. And I'll share my screen. Can you see my screen?
Yes.
Yeah.
Okay. Good morning, everyone, or good evening from us in China. And we're really happy to be here today. Many thanks to the Temporal Graph Learning Reading Group for the kind invitation and for giving us this opportunity to share our work. Today, Wailing and I will present our ICLR 2026 paper, UrbanGraph, Physics-Informed Spatial-Temporal Dynamic Heterogeneous Graph for Urban Microclimate Prediction. We're very happy looking forward to the discussion and to hear your thoughts. Before going into the technical details, I'd like to briefly position this work. Our background is a bit different from a typical computer science group. We're mainly from architecture and urban science. So we start from a real urban physical problem where many processes are continuous physical field shifted by urban geometry and material and environmental dynamics. The challenge is how to turn such continuous physical fields into efficient, physically meaningful AI representations. And this is the motivation behind UrbanGraph. Well, here's the roadmap for today's talk. I will start with the problem and research gap, and then introduce our physically informed graph representations. Basically, how we translate our urban physical interactions into graph topology. Wailing will then take over for the second half of this talk, focus on the model design, experimental result, and the future directions. Let me start with the first part. Urban microclimate matters because it directly affects how people experience heat in cities, especially under the trend of the climate change. To quantify the human heat exposure, we actually use the UTCI, which is the Universal Thermal Climate Index at the prediction target. But UTCI is difficult to model for two reasons. First, it's spatially heterogeneous. Like buildings, trees, and land cover can actually create a different local environment within the same neighborhood. Second, it is temporally dynamic, like solar radiation, wind, air temperature, humidity change continuously over time. More importantly, these factors do not work independently. They are coupled through physical process such as radiation, shading, convection. So the challenge is not to predict a value, but to capture how these coupled physical process evolve across space and time. Um, from a learning process, we can think of urban microclimate prediction as a spatial-temporal physical field learning problem. The input includes historical graph states and dynamic weather forcing and the static GIS features, which is the geographic information system features. The goal is to predict feature fields such as UDCI, wind speed, or temperature. But this formulation is broader than microclimate. More generally, it's about predicting how physical fields evolve over space and time under structured spatial interactions. This also like connected to the problem like the weather forecasting, flood modeling, wildfire spreading, and air quality explosion.
Uh, can I ask a quick question on the formulation?
Sure,
So for
please.
the global context vector is a graph level feature. The static GIS feature is a node level feature, right?
Yes.
And then for the historical graph, does the number of nodes stay fixed?
Um, the number of nodes they fixed. Um,
Is that the assumption or
Yeah,
it,
yeah, yes. The number of nodes will fixed during the whole representation process. Yeah.
okay? And the edges will change a lot, or do you know just out of curiosity, does the edges change a lot, or
Uh,
they still
uh,
yes.
stay mostly consistent?
you mean the age?
The edges.
The edges, yes, the edges will change during the different time steps. Yeah.
Okay.
Yeah.
And then for the final prediction, it's gonna be a graph level prediction, right?
Yeah, kind of graph level, but also the grid based. Because our task is, the physical fields is like the urban morphology is grid based. So our results also the grid based. Yeah. But each grid it is a node actually. Yeah.
Oh, okay. So it's a node level prediction. Okay. Thanks.
Right.
Thanks for the clarification.
Is a follow-up question, is there any like real world interpretation to what the nodes here are? Is it like weather stations or something like this?
The note that is real world interpretation is actually could represent the geographic information like building, like land cover and trees. Uh, yes, I
Okay.
will explain it in later slides.
Okay, then I'll wait. Thank you.
Thank you. Um, so next. So given such complexity, one natural solution is to use high fidelity physical simulations such as CFD tools, which is computational fluid dynamics, to solve the urban microclimate in such physical field. These simulations can be very accurate, but because they explicit model the physical process, but they also computational expensive. In urban application, this become a major bottleneck, which is every new geometry, weather condition, or design scenario may require another full simulation. Standard machine learning models are much faster, but they often miss the physical structure of the problem. So our goal is to build the scalable surrogates that are both computational efficiency and physically meaningful. After discuss the course of physical simulation, let's look at the standard learning models. The grid-based deep learning, which, for example, CNN-based models, are computationally efficient, but they rely on local grid neighborhoods. So they cannot model long-range directional or non-local physical interactions. Well, standard GNs are more flexible for spatial dependency, but their graph structure usually do not explicitly reflect the physical process. So the key question is, can we construct graph representation that align with the physical process in the urban environment? More recent methods have already addressed part of this question. For example, physical informed machine learning has physical knowledge, but the physical laws, often make the training more difficult and expensive. Well, the heterogeneous graph learning introduced different relation types, but these relations are not always physically meaningful. And the dynamic graph capture evolving interactions, but the evolutions often learn from data rather than directly driven by physical laws. So the gap is clear. We need graph topology that is physical, relational, and time varying at the same time. We now move to the core idea of the urban graph, encoding the physical causality directly into the graph representation. The main design principle is that physical defines the graph before neural message passing. We start from physical rules such as sun angle, wind direction, and vegetation effects. These rules used to prompt candidate link and keep only physically plausible causal edges. The remaining edges from the heterogeneous topology where different edge types represent different physical process. And then message passing is then performed only along these physical plausible maps. This is different from implicit graph learning. In implicit graph learning, the model tries to infer the adjacency from data while also learn the prediction task. In urban graph, physical rules and weather condition first define which interactions are plausible. The model then learn the prediction function on the constrained graph. So the graph is not fully discovered from data. It is specified by physical causal structure. We represent each time step as a dynamic heterogeneous graph. Formally, GT is defined by three components, V, ET, and R. V is fixed. It represents urban entities such as building, land cover, and trees, basically what exists in the city. ET is dynamic. It changes with weather and time. It tells us when and where the interaction happened. And R represent relation types, such as shading, convection, radiation, and vegetation effects. It tells us which physical process each edge corresponds to. In this way, urban graph predicts how the target microclimate field, such as UDCI, evolves over time. Here we define 5 edges to encode urban physics. We divide them into 2 groups, dynamic physical edges and static structural edges. Dynamic physical edges change with external forcing such as solar position, vegetation effects, and wind conditions. Well, the static structural edges are determined by the urban form itself. They include semantic similarity and internal contiguity. Together, these edge types represent different physical or structural mechanism in the graph. The first dynamic edge is shading edge. If a building or a tree casts shadow on the ground node, we create a direct edge from the object to the shaded node. These edge changes over time as the sun moves. The direction and the length of the shadow also change. So the same building may affect different ground nodes in the morning, noon, and afternoon. This makes shading edge dynamic and directed. Next, we move to the vegetation evapotranspiration edges, which means that vegetation cools the surrounding air by releasing water vapor. Here, the vegetation nodes are connected to the nearby target nodes within an activity radius. This radius actually represents the local cooling neighborhood around trees or vegetation. The radius changes with weather conditions. Under stronger sunlight, the cooling effects become stronger, so the neighborhood becomes larger. Under the weaker sunlight or the cloud cover, it becomes smaller. Then we go to the convective diffusion edge. This edge describes how airflow is transported by the local wind field around buildings. When the wind direction changes, the local field pathway also changes. For example, the east wind and the south wind create different, the downstream region. So the active graph edge are different. In this way, the convection diffusion edges are also dynamic and directional. They allow massive passing to follow the wind-dependent transport paths rather than use a fixed neighborhood. Now we move to the dynamic physical edge, to the static structural edge. The first one is the semantic similarity. It does not change with the weather or the time. The idea is to connect the nodes with similar surrounding urban context, even if they are far apart. For example, two locations may have similar building layouts and the vegetation patterns, so they can share the useful information. These allow the model to go beyond local neighborhoods and learn from the non-local but structurally similar urban touches. The last edge type is the internal continuity. This is also a static structural edge. It connects nodes that belongs to the same continuous physical objects, such as one the vegetation patch or one connected building surface. The importance is that we only connected cells within the same connected component. We actually do not connect separate objects, even if they are close to each other. This helps the model preserve local physical continuity inside one object, instead of treating all the grid cells as independent points. Now that we have defined our physical informed graph structure, I will hand over to William to explain how UrbanGraph term learns from the dynamic heterological sequence. William.
Okay. Can you see my screen, right?
Yes.
Yes.
Okay, yeah.
Yeah.
So earlier, we have already explained how we construct urban entities and physical processes at the dynamic heterogeneous graph. So the next step is to learn the spatial interactions and temporal evolution on these time series graphs. In this way, we can learn useful features for each node and then use them for prediction. And the overall architecture of UrbanGraph is quite simple, quite straightforward actually. First, we feed the constructed dynamic heterogeneous graph into the RGCN block to extract the spatial features. And then we fuse the extracted spatial features with the global information like time embedding and climate features embedding. And the next step, we feed the fused features into the LSTM model to capture the temporal patterns. And finally, we passed the render features through a linear layer to make the prediction. And yeah, and next I will explain each part of the architecture in more detail. So the first module we use is RGCN block. As we mentioned earlier, we encode different physical process at different age types, such as shading, vegetation evapotranspiration, and the convective diffusion. So we use RGCN to assign a separate parameter matrix to to represent different relation type. And this help avoid physical operator entanglement. For example, you reduce the conflict between like radiation shading and fluid convection during the message passing process. And after the RGCN extract the spatial features, we concatenate these features with the global and time features. Then we pass the concatenated features through an MLP layer and feed them into the LSTM layer. And we place features fusion after the RGCN block because we want to avoid global features smoothing out the difference between nodes. And in addition, we use the feature extraction. We use the feature extracted by the RGCN at the initial time step to warm up the LMS layer. So this gives the hidden state a better starting point. Although the dynamic graph at different time step already have the temporal continuity in their graph structure, we still need to add a continuity constraint to the final features extracted at each time step. This is because microclimate changes are continuous by nature. They shouldn't suddenly jump between like neighboring time steps. For example, if the temperature of a surface increase from 30 Celsius degrees to like 32 Celsius degrees, it shouldn't suddenly drop to 10 Celsius degrees in the next step without a clear reason. So we use LSTM to model the temporal evolution. Actually, its cell state can be understood as a kind of temporal memory. It keeps the thermal state from the previous time step and gradually update it to the next time step. And in this way, the model can maintain continuity over the whole time window. And now let's move on the experiments and the result parts. So first, let me introduce the dataset and our experimental setup. Our dataset is generated from high fidelity physical simulation using AVMAT, which is a physical-based simulation engine. By providing static features and meteorological features at input, we can obtain the target variables we want to predict, such as UTCI and air temperature, wind speed. And in the simulation, the spatial resolution is 4 meter horizontally and 3 meter vertically. So actually, the datasets can provide a relative fine-grained urban microclimate field. And our simulation period is from 8 a.m. in the morning to 19 p.m. And our whole simulation is during an extreme whole day in Singapore and covering this 12 hours in total. So focusing on the extreme whole days help us identify the worst case conditions, which can better support the decision-making process, like the urban design. So in terms of scale, the dataset includes around 400 spatially different urban blocks with about around 12 million spatial temporal data points in total. And these blocks cover diverse urban forms. So during the evolution process, our test set is composed entirely of spatially unseen urban blocks. So this helps us test the generalization ability of our model. In our experiment, we used 4 groups of baselines. The first is grid-based model, and then static STGNS, and then generative graph models, and the dynamic graph models. So this design helps us answer several questions. So first, is the graph structure more suitable than a grid structure? And second, is the dynamic typology better than a static typology? And third, is an explicit physical-based typology more effective than the implicit graph learning? And we evaluate our different baselines and our architectures using all these metrics like MA, RMC, flops, and our inference time. So let's first look at the main results. We can see our urban graph achieved the highest average R-square values, outperforming the representative baselines listed here. And besides our urban graph itself, its two variants, the RGCN GRU and RGCN transformer, also perform better than LRGCN, which is the strongest dynamic graph baseline. And GE-LSTM is the best performing model among the baseline outside our own architecture. In contrast, the soft constraint physical informed method, peaks-to-peaks with PIN, perform worse, and the gray space method show the weakest performance overall. By analyzing the trade-off between accuracy and efficiency, we can see that UrbanGraph is not only the most accurate model, but also has much lower flops than like the dynamic graph baseline, LRGCN. And compared with this architecture, UrbanGraph reduced flops by like more than 70% and improved training speed by 20%. And compared with the implicit learning methods mentioned above, the main reason for our improvement in both accuracy and efficiency is that we prune impossible connections before the data enter the neural network. And this pruning is based on our physical process, our physical rules, and all these hard physical constraints. And in this way, we reduce the hypothesis space and also lowers the computational cost of later, the message passing process. And this provide our architecture have the advantage of explicit physical based typology. And compare with peaks-to-peaks with PIN, which as physical as a soft constraint in the loss function. Our architecture introduced physical constraints at the typology level, and this leads to better prediction accuracy. And this results show that for urban physical fields prediction, embedding the physics into the graph topology is effective, and it can also achieve better results than using physics only as a such constraints. And next, we visualize the prediction result at different hours. We can see that compared with other baselines, our method is not only better at predicting the overall average pattern like the R-square values, but also better at recovering spatial details, such as this local height and cold difference around buildings. And the main errors are concentrated near some building boundaries and area with the strong local gradient changes. But even in these regions, our method still perform better than other baselines. And we also compare the prediction performance across different hours. One thing worth not noting is the afternoon period, especially around 2 p.m. and 5 p.m. During this period, the solar radiation, wind, and the local summer environment change more strongly. So as a result, many models have larger error fluctuations. And our performance, our architecture performance is relatively more stable. And this suggests that the dynamic physical typology helps reduce error accumulation in temporal prediction, and it also improve the robustness of the model across different time periods. We further compare it with models trained separately for each hour, and this comparison confirms the necessity of temporal modeling. We also conduct a lot of ablation studies, and the key component of our architecture. So if we use a homogeneous graph, the performance drops by around 3.4%. And if we further remove the dynamic mechanism, the performance drops by another 6.6%. And here, for the homogeneous graph settings, we replace the RGCN with GCN. And for the static graph settings, we use the graph structure from the initial time step for prediction at all the following time steps. And we also find that removing global features has a large impact on performance, and the R-square values will drop from 0.86 to 0.71. And the age ablation study show that removing any type of age will affect the model performance. If we remove the shadow age, the R-square values will drop to 0.82, something like this. And we also conduct the ablation studies on node features, and we find that using only the average features of neighbor nodes give the best performance. And if we adding the graph structure features such as the node degrees, actually will hurt the performance. And one reason explanation is that we have already constructed a physically consistent graph structure. So additional structure features don't help much. Instead, they may introduce extra noise. And to validate the general applicability of UrbanGraph, we extend the prediction task to multiple microclimate variables. The physical mechanisms behind these variables actually are not exactly the same. For example, wind speed depends more on fluid dynamics, and MRT depends more on radiative transfer, and PET and UTCI are more comprehensive human thermal comfort indicators. And we can see that the UrbanGraph achieves relatively stable performance across these variables, and in particular, the R-square values for the these three parameters, MRT, PET, and UTCI, are quite high. This is because the typology we construct for UTC prediction is most closely relative to these three variables. And in this experiment, in this validation process, we keep the same graph topology for all these three parameters prediction. And we use the training model to make predictions for the whole of Singapore and validate the result using one open source dataset. And in our scalability test, we found that as the number of edge increase, both inference time and GPU usage grow almost linearly. So this shows the feasibility of using this architecture for large-scale physical field prediction task. And we also conduct a cross-domain generalization test. Here we further test whether our architecture can be transferred to another related but more purely physical field problem like 3D vector wind field prediction. And from this comparison, we can see that UrbanGraph achieves an R-square values of 0.88, which is clearly higher than the standard graded GCN architecture. And this again shows that the whole framework provides an effective solution for this type of like the physical field prediction problem. Although our work achieves the best results on the type of prediction task, it still have some limitations. And the limitation is about the trade-off between physical consistency and the latent discovery. On the left side, we show the current strengths of our framework. We explicitly encode non-urban physics process into the graph structure. However, the downside is that some latent relationships that are not modeled by us may be ignored. So this could further affect the prediction performance. So one further direction is to add a sparse learnable residual graph on top of the physical typology. This should allow the model to keep physical consistency while still discovering latent relationships that are not, not explicitly modeled. And the value of this sparse residual graph is not only to improve prediction performance by analyzing the learned graph structure, we may also reveal unknown patterns in urban physical fields. So in this way, our task can move beyond prediction and become a step toward to the scientific discovery. So to summary, the core idea of UrbanGraph is to transform first principles in continuous urban physics field into a dynamic causal typology for graph learning. And instead of starting from a dense graph with unclear physical meanings, we actively prone physically unreasonable connections based on the physical mechanisms. In this way, we construct a sparse and more physically consistent heterogeneous graph, which improve both accuracy and efficiency. So this work showed that for spatial-temporal systems driven by clear physical laws, the graph typology itself can serve as a strong inductive bias. And we also hope that future graph-related research can pay more attention to how the graph structure itself can better reflect real-world physical interactions. So yeah, that's all. That's what we sharing for our paper. Thank you for your listening.
Yeah, thanks for the great presentation. Super nice presentation also. I don't know how you guys made the slides, but we can discuss that maybe after the technical questions.
Okay.
So I do have a question. So you mentioned that, and I also checked the paper that you have kind of explicit ways to construct the edges based on physical meaning. It's very interesting. But have you think about what if you don't use a GNN that does explicit metric passing, but you feed the graph as implicit positional encoding? Basically, you compute the positional encoding from the graph that you pruned, and you feed that into a graph transformer, do you think that would give you better performance? And potentially the transformer can learn to attend over specific connections that might be pruned, but still might be useful for connectivity, even if it doesn't have physical meaning. Does that make sense?
Yeah, I think this is a good question because transformer should be better than um other architecture, right? Because transformer can learn all kinds of connections, all in all possible connections. So, but the key is um, we also have to consider the efficiency. So yeah, because for the task of in our field, um, actually the efficiency is quite important because we have a very large urban morphology. You know, in our study, the resolution of each node represent 4 meter by 4 meter. So you can imagine how much nodes will have if we would like to represent the whole city. So
Do you know a rough estimate about how many nodes there might be?
in our work, one block like 2 kilometer by 2 kilometer, and we will have more than 60K nodes. And
Okay, so then the whole city will potentially be tens of millions of nodes.
yes, more than something like this. Yeah.
But I
So
think in this case, it could be also interesting because you
yeah,
you don't have to assume that every single of these nodes have to connect with every
yeah,
node. Then you
yeah.
can have a block constraint transformer or something like that. You can have a sparse
Um,
transformer that bake kind of this block structure into the transformer so that it's also
mm,
efficient, while it can still learn potentially connections that's useful within the block.
um,
Potentially,
okay,
just
okay, yeah.
think about it.
We'll try about that. Thank you for suggestions. Yeah.
Um, yeah, and then it also depends on how you do the positional encoding, I guess, because as soon
Mhm.
as you do positional encoding, you will lose information. So the GNN preserve the most information because you be the graph as is, but how you choose to use positional encoding like also plays an effect. So I wouldn't say that using a transformer definitely is more powerful, but I think
Mhm.
there's a lot of interesting research that maybe you can try.
Yeah.
And because it's not clear to me if based on physical meaning, you're removing the edges, like the removed edges might not be physically plausible, but it might be useful for neural network to learn the embedding better. For example,
Mm.
it can do shortcuts between more distant nodes and these kind of things.
Yeah. Yeah.
But but yeah, super nice work, and I will let others ask questions as well.
Yeah. Thank you.
Thank you.
Thanks.
I was a bit curious. So during the training of the model, right, it seems like you have different predictive tasks on different weather phenomena.
Yeah.
So how did you weigh these? Like, did you train with a similar loss or weigh it equally, or?
Uh, sorry. Train the same laws. You mean the loss function or?
Yeah, so can you elaborate a bit about the loss function of the model when you're training with different predictive tasks, right?
Yeah. We use the same loss function actually. I think maybe should be the MSE loss.
Okay.
So it is quite straightforward because our task is node prediction.
Mhm.
The regression task. So we have for each node we have the ground truth value and we have the prediction value. So we can use this to give the feedback to train our base. Yeah.
Okay, so it also seemed like you had different predictive tasks, right? So for each
Yeah.
node, you would have, one measurement of, I don't
Yeah.
know, humidity and one
Yeah.
measurement
Yeah.
of
Yeah.
this. Are they on the same equivalent scale? I'm just like if the model is biased towards being good in one domain, but maybe worse in another, or how you deal with this?
Okay, so you can find in this graph, right? For the MRT, PT, and UCI, actually the R square value is acceptable, but for the RH, wind speed, air temperature is relatively lower, right? This is because we use the same typology. We use the same physical laws to train all these six models. Actually, each parameter we train the model
Yeah.
once. Yeah. Cause our main task is to predict the UTCI, and UTCI is the indicator that combine a lot of parameters like air temperature, wind speed, and MRT. And for example, the MRT is directly relative to the shade. If you directly in the sunlight, the MRT will very high. But if you in the shading, the MRT will low. So actually, as we mentioned before, we create 5 types of edges, and in this 6 training process, we still use the 5 type of edges. For UTCI and PT and MRT, all these parameters is more relative to our age, our physical laws, our defined physical laws. But for air temperature, actually air temperature is don't have a lot of relation with the shade, because air temperature is just air temperature. Air temperature at shade will be the MRT. So maybe this is more easily to understand. Yeah.
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 I was just curious how much tinkering you guys had done with the loss function, or if it was kind of
yeah. Good question. Thank you. Thank you.
Of course. Thank you.
Thank you.
Cool. I think that's the question for now. And thanks a lot for presenting again. It's super nice work. And again, I don't know how you guys made these diagrams, but it's very good. If you have recommendation or suggestions, be very
Can we talk about this? I wrote in the organizers channel that sometimes slides can be distracting because they're too ugly. I feel like in this presentation the slides were distracting because they were too beautiful.
Yeah. Well,
Please
thank you.
elaborate.
Yeah.
Well, actually, we integrate many, the large models. We use the Gemini for to generate the stretch, and we do a lot of model it and use image2 from GPT to unify the style. So under some the quality control, it will be the
Yeah, I think you can do a startup just based on this. I feel like people would pay to subscribe to make nice diagrams.
So just out of like the images that I'm looking at here, have they been through like a visual language model or?
Yeah. Some images should be based on the visual language model. Yeah.
You can tell a little bit, but it's not. But I think the
I think
actual.
Chenyu can explain more about the diagram. Yeah.
Okay, okay.
well the such the colorful heat map is actually derived from our simulation tools. We actually use the generative model to to read our paper and give us some the layout suggestion, and we put the suggestion in try it in different platform, like some the mature platform like Gemini, and we also use some open source PowerPoint, a slice generator to do lots of icon or something. And finally, we need to the uniform. It's like the font size and the style manually, so it could be yeah.
Very cool.
Yeah, very nice.
Yeah, thanks for sharing that. And then if any time in the future you decide to open source your workflow for generating diagrams, I will be adding more stuff. Yeah, thanks.
Yeah.
Otherwise,
Thanks.
you know who's a paid customer, right, Andy? Like not necessarily open source, just make a startup out of it.
That also works.
Yeah.
Okay.
Cool.
Cool. Thanks everyone. And thanks again for presenting. Okay, so let's wrap up here today then. Yeah.
Okay, yeah.
Thank you. Thank you
Thank
very
you
much.
very much.
Thank you.
For such
Thank you.
impressive